So now we look at each case here of each configuration type. We'll start with the RC low pass filter. Again, a lot of this is going to look like stuff you've already learned. It's just a matter of applying it now in the sense of it being a filter. You've already seen what happens with resonant circuits. So we're just applying those fundamentals. Okay, don't get intimidated by this. You're just applying them. You're going to see some manipulations with the relationships, but we're still doing the same thing. So in this case, as you can see from the circuit below, we've got an RC network, or an RC circuit. Okay, we've got the output being taken across the capacitor in this case, and what it forms is an RC low pass filter. Notice the output voltage taken across the capacitor. When the input is DC, or not a non-sinusoidal input, 0 hertz, the output voltage equals the input voltage because X sub C is infinitely large. So all you have is just the effects of the resistor and in the input and the output. As the input frequency then starts to increase, so we start moving into the sinusoidal realm, the AC realm, X sub C decreases, and as a result, V out gradually decreases until a frequency is reached where now X sub C equals the total resistance. Okay, so we have the reactive component equaling the pure resistive component. This is the critical frequency F sub C of the filter. So in this case then, we start with X sub C from using the familiar expression 2 pi times FC times C, and we set both sides equal to each other. Okay, so we have essentially X sub C equals X sub R, but we know that X sub C equals 2 pi FC. So in this case, we can manipulate the relationship and solve for the center frequency, or the critical frequency. So the critical frequency becomes 1 over 2 pi RC now. So we just manipulated it so that we are allowed to solve for other unknowns. So at any frequency, by application of the voltage divider formula, again, if you haven't gone back and refamiliarized yourself with the voltage divider formula as you learned it in ET131, go back and look at it, and then come back and look at this, and you'll see it's the same relationship. But now we're using the reactive terms, okay, and the vector or phasor term here in the denominator. The output voltage magnitude then becomes X sub C by the sum of the squares, the square root, times V sub n. Since X sub C and R at the critical frequency, the output voltage at the critical frequency then can be expressed as, so you see they made the substitution. Since R and X are the same, let's just substitute the value of R in here. So now we have all purely resistive terms in our voltage divider formula. So we have R divided by 2 times R squared. We sum these two R squares together, take the square root. So in this case, we can factor out the R. We're left with the square root of 2 times Vn, or 1 over the square root of 2 times Vn, which gives us now the familiar 0.707 that we learned previously. These calculations show that the output then is 70.7% of the input when X sub C equals R. The frequency at which this occurs then by definition is what we call the critical frequency. The ratio of the output voltage to input voltage at the critical frequency can be expressed then in decibels. So now we go back to our decibel relationship for voltage. Voltage out is equal to 0.707 times voltage in. Since V out over Vn then equals 0.707, we can substitute that into our relationship for the ratio of V out over Vn, and we have 20 times the log of 0.707, and here now we see where we come up with our negative 3 dB as the response. Notice that we're using the terms now that we should be becoming familiar with. So go back over this relationship and this manipulation, this derivation, and make sure that you understand it. So minus 3 dB. So let's look at another quick example. Okay, this is what we just did here. Determine the critical frequency, then V out at the critical frequency for an input of 10 volts for an RC low pass filter. So now we can see there's where we started. X sub C equals R. Substitute in here 2 pi the critical frequency times the capacitor. Enter your values from your circuit. We end up with F sub C then equal to 3.38.6 kilohertz. Look at our voltage divider relationship. Again, knowing that X sub C equals R at the critical frequency, 338.6 kHz, we make the substitution then for R into X sub C, simplify the expression, and what we come out with, just like we saw previously, is 0.707 times the voltage in. So if we look at plotting then the dB output, notice now we have on the y-axis here a plotting in decibels, V out over Vn in dB. The blue line in the figure shows an actual response curve for a low pass filter. So you can see we've got what we would typically measure, say on an O-scope. If we could make that measurement, that we would have what we call the knee right here of the ideal change that would occur instantaneously. We know that our responses do not change instantaneously. The maximum output then is defined to be 0 dB. So that's right on the line here, 0 dB on the y-axis with a change in the frequency. Okay, 0 decibels responds to V out equal to Vn, because 20 times the log of V out over Vn is equal to 20 times the log of 1. The log of 1 is 0. If you don't believe it, pull out your calculator, enter 1, hit log, and you will see that you get 20 dB. Write that down in your notebook. That's something to remember. The output drops then from 0 to minus 3 dB, and you can see that on the trace here on the blue line at the critical frequency, and then continues to decrease at a fixed rate. The pattern of decrease is called the roll-off of the frequency response. The red line shows an ideal output response that is considered to be flat out of the critical frequency. The output then decreases at a fixed rate. Okay, so what we're starting to see here now is what I promised you. We're going to start looking at developing what are called Bode plots for our response curves for our circuits. So as you've seen, the output voltage of a low-pass filter decreases by 3 dB when the frequency is increased to the critical value F sub C. As the frequency continues to increase above F sub C, the output voltage continues to decrease. In fact, for each tenfold increase in frequency above F sub C, there is a 20 dB reduction in the output, as the following step shows. So let's take a frequency that is 10 times the critical frequency. So we create an expression, frequency is equal to 10 times the critical. Since R is equal to X sub C, then, as we've seen before, at F sub C, then R is equal to 10 times the the reactive component for the capacitor at 10 times F sub C, because the inverse relationship of X sub C and the frequency. Okay, inverse relationship of X sub C and frequency. So the attenuation is the reduction of voltage expressed as the ratio V out over Vn and is developed as follows. So here's the mathematical relationship. So V out over Vn, we set that equal to X sub C over the phasor sum. We get X sub C is equal to 10 times X sub C plus X sub C2 in this example where we're trying to show that we have a 20 dB reduction. So now X sub C over the phasor sum of 10 times X sub C squared by X sub C squared gives us then, when we factor X sub C out, 100 plus 1. So what we end up with then is X sub C. When we take the square root of X sub C, we're left with X sub C. So those two terms cancel out. We end up with 1 over the square root of 101, which we can say is approximately equal to 1/10 or 0.1. So the dB attenuation, 20 log V out over Vn, is equal to 20 log of 1/10, 0.1, or minus 20 dB. Okay, this is an important concept that you understand. If this is going over your head right now, stop, go back, reread it in your text, look at my explanation here as we've progressed through it, because this is a very important understanding. Once you understand it and you believe it, then you can let it go. When you see it again, you will just accept it. So the tenfold change in frequency we call a decade. So for an RC circuit, the output voltage is reduced by 20 dB or 20 dB per decade. For each decade increase in frequency, a similar result can be derived then for a high-pass circuit. The roll-off is a constant minus 20 dB per decade for a basic RC or RL filter. So the diagram shows that the ideal frequency response plot on a semi-log scale, okay, if you're not familiar with semi-log paper or semi-log scale, go back and take a look at that. It should be something that you've seen before, where each interval on the horizontal axis represents a tenfold increase in frequency. This response now we call the Bode plot, and you'll be seeing it more now in the rest of this course and in future courses. So if we take a look at make a Bode plot of the filter for 3 decades of frequency. Okay, so we've got this filter that we've looked at before. In this case, we are going to calculate what the critical frequency is. So we enter our components for R and C and calculate 33.9 kHz as the critical frequency. Okay, so in this case, the idealized Bode plot is shown with the red line on the semi-log graph in the figure. The approximate actual response curve is shown with the blue line. Notice first that the horizontal scale is logarithmic and the vertical scale is linear. The frequency is on the logarithmic scale. The filter output in decibels is on the linear scale. So you've got a mix here. This is your semi-log paper. The output is flat at 33.9 kHz, the critical frequency. As the frequency increases above the critical frequency, the output drops at a rate of minus 20 dB per decade. Thus, for the ideal curve, every time the frequency is increased by 10, the output is reduced by 20 dB. A slight variation from this occurs in actual practice, but the output is actually at minus 3 dB rather than 0 dB at the critical frequency. So make sure you understand this. Go back, look at it, read it, work it out, because this is very important. So in the next one, we'll take a look at how the same thing occurs in an RL low-pass filter.